So we're going to be looking at enthalpy changes during dissolution or when we're dissolving things. Okay. The first enthalpy change that we're going to look at is the enthalpy change of solution. The enthalpy change of solution. Now the enthalpy change of solution is the enthalpy change when one mole of a solute is dissolved in sufficient water to form an infinitely dilute solution. To form an infinitely dilute solution. Okay. And sometimes you're going to see that instead of solute, it'll just be solid given to you over here. Okay. Normally, when we're talking about enthalpy changes of solution, we're talking about the solution of ionic solids or dissolution of ionic solids. But enthalpy change of solution just generally refers to the enthalpy change when one mole of a solute is dissolved in sufficient water to form an infinitely dilute solution. Now, it's a theoretical thing, but the idea here is that you have 1 mole of a solute dissolving in a very, very, very large amount of water. So you can think of like 1 mole of sodium chloride dissolving in like a swimming pool full of water, right? Because you can't really have an infinitely dilute solution, right? Because when we say infinitely dilute, it's undefined, right? Infinity itself. But the idea here is that we have a very large amount of water and we're making a very dilute solution. Okay, so the enthalpy change associated with that is the enthalpy change of solution. And it's usually endothermic. Okay, it is usually endothermic. So here again, you can think of like an everyday example, like dissolving salt in water, right? We know that more salt will dissolve in hot water. So higher temperatures favor solubility in most cases. And if higher temperatures favor solubility, that means that dissolving itself must be endothermic since higher temperatures favor it. So here's an example, right? We have sodium chloride solid, okay, dissolving in water to form aqueous ions, okay. The enthalpy change associated with this reaction is the enthalpy change of solution. So we're just adding it to water, right? We're just adding it to water here. And this is the enthalpy change of solution of sodium chloride. Again, when we're talking about enthalpy of solution, we're talking about 1 mole of that solute or 1 mole of that solid dissolving to form an aqueous solution. The next enthalpy change that we have is the enthalpy change of hydration. The enthalpy change of hydration. Okay, what is the enthalpy change of hydration? The enthalpy change of hydration is the enthalpy change when 1 mole of a gaseous ion dissolves in sufficient water to form an infinitely dilute solution. Okay. So enthalpy changes of hydration are always exothermic. The reason they're always exothermic is because we're starting with gaseous ions, which are highly unstable, highly reactive at a very high energy, to form aqueous ions. These gaseous ions are dissolving in water to form aqueous ions. Aqueous ions are relatively stable, okay? So they're relatively low energy. So you're going from a very high energy gaseous ion to a relatively low energy aqueous ion, right? So therefore, there's going to be energy released, okay? The enthalpy change is negative. So enthalpy changes of hydration are highly exothermic, okay? And again, when we talk about enthalpy changes of hydration, we're talking about the hydration of specific ions. So the enthalpy change of hydration of Mg2 plus ions, for example, will be from magnesium gaseous ions to magnesium aqueous ions. Again, you can write H2O here, or you can just write aqueous, like AQ. That just means that you're adding them to water, okay? So this equation here represents the enthalpy change of hydration of magnesium ions. Similarly, this represents the hydration of chloride ions. Okay, so when we talk about hydration enthalpies, we're talking about specific ions going from the gaseous state to the aqueous state. The enthalpy changes, or the energy released when a specific gaseous ion goes from the gaseous state to the aqueous state, or a specific gaseous ion dissolves in a very large amount of water to form a very dilute solution. And again, we're specifically referring to 1 mole of that gaseous ion dissolving when we're talking about the enthalpy of hydration. So obviously for enthalpy change of solution, we can use delta H SOL, right, or delta H solution. And for enthalpy change of hydration, we just use delta H HYD. Okay, that's hydration here. So what I want to think about now is how can we calculate the enthalpy change of solution using enthalpy changes of hydration and the lattice enthalpy. So for example, let's start with sodium chloride in the solid state. Okay, let's start with sodium chloride in the solid state, right? So here I have a lattice of sodium chloride, right? I have solid sodium chloride. Now what I want to do is I want to dissolve sodium chloride in water, right? When sodium chloride dissolves in water, I have these free aqueous ions, right? I have the sodium cation surrounded by water molecules, and I have the chloride ion over here also surrounded by water molecules in aqueous solution. Now we know that when we dissolve sodium chloride in water, that enthalpy change is the enthalpy of solution. It's usually endothermic, and in the case of sodium chloride, it is endothermic. We know that more salt dissolves at higher temperature. So we know that this enthalpy change is endothermic. And we have sodium aqueous ions over here and chloride, aqueous chloride ions as well. So one way to think about dissolution is the following. Think of the solid lattice. Okay, we're starting with sodium chloride solid and we're dissolving it in water to form these aqueous ions. And one way to think about this in a theoretical way is that what we're first doing over here is we're breaking apart the ions in sodium chloride completely to form gaseous ions. So we're completely separating the ions in sodium chloride to form gaseous ions. That is sodium gaseous ions and Na plus gaseous and Cl minus gaseous ions. Right? So what we've done is we've taken this lattice and we've completely separated the ions to form gaseous ions. And then we're dissolving those gaseous ions in water to form an aqueous solution. Right? Now we know that the change from gaseous ions to solid lattice is the lattice enthalpy. This is the lattice enthalpy by definition, right? The lattice enthalpy is the energy released when 1 mole of a solid lattice is formed from its constituent gaseous ions. So the reverse, by convention, the reverse will be the negative lattice enthalpy. So we can say that this is negative delta H lattice of sodium chloride. So what we've done is we've taken the solid lattice, we've completely separated the ions to form gaseous ions. That is the negative lattice enthalpy. And then those gaseous ions have been dissolved in water to form an aqueous solution. That is the hydration enthalpy of the ions. So what we have here is we have hydration of sodium ions plus the hydration of chloride ions. The reason we've drawn this theoretical framework here is so that we can find a relationship between the enthalpy of solution, the lattice enthalpy, and the hydration enthalpy. So one way to think about this is that if we start with a solid lattice, right? If we start with a solid lattice and we directly dissolve it in water, that's the enthalpy change of solution. That enthalpy change over here, that is the enthalpy change of solution, is equal to the negative lattice enthalpy, that is the energy needed to separate the ions in the solid lattice to form gaseous ions. So that is a negative lattice enthalpy, plus the hydration enthalpies, of sodium and chloride. So if we rearrange this expression, we can say that the enthalpy change of solution is equal to the sum of the hydration enthalpies minus the lattice enthalpy for any ionic compound. Okay, if we start with any ionic compound, if we dissolve it in water, that's the enthalpy change of solution, right? And that is equivalent to separating that is equivalent to separating the ions in the solid state to form gaseous ions and then dissolving those gaseous ions in water to form an aqueous solution. So the enthalpy change of solution is the lattice enthalpy, the negative lattice enthalpy plus the hydrations of the individual ions. Here we just have 1 mole of sodium ions and 1 mole of chloride ions. So we just have hydration of sodium plus hydration of chloride. If we add those up and subtract the lattice enthalpy, we would get the enthalpy change of solution. Now, one last thing to note over here is that the lattice enthalpy, by convention, we said is the enthalpy change or the energy released when 1 mole of an ionic solid is formed from its constituent gaseous ions. So the way we define it, we know it'll always be exothermic, because when gaseous ions come together, right, very strong ionic bonds are formed, and we know that bond formation releases energy. Now, why is hydration exothermic? We know gaseous ions are at a higher energy and aqueous ions are at a lower energy. But really what's happening is that the reason why aqueous ions are at a lower energy is because when these gaseous ions are dissolved in water, the water molecules, those polar molecules, they form forces of attraction, strong forces of attraction with the cations and the anions. So over here we can see that the oxygen in the water molecules form forces of attraction with the sodium ion here, right, with the cation. Similarly, the delta positive hydrogen, the partially positive hydrogen atoms in water molecules form forces of attraction with the anion, the chloride ion in this case. And these forces of attraction, right, these bonds that are forming or these attractions that are forming between water molecules and the ions result in a release of energy. Okay, that's why hydration is always exothermic. Now this energy cycle here can also be visualized using a Hess cycle. What we want to do here is we want to find the enthalpy of solution of sodium chloride. So we're going to start with solid sodium chloride and we're dissolving it in water to form aqueous ions. So that is sodium aqueous ions and aqueous chloride ions as well. And what we want to do is we want to find the enthalpy of solution in terms of the lattice energy and the hydration enthalpies, or the lattice enthalpy and the hydration enthalpies. So we know that over here we're going to have the gaseous ions, since lattice enthalpy refers to the formation of the solid lattice from gaseous ions. So we can say that this is the lattice enthalpy. And this arrow here represents the lattice enthalpy from gaseous ions to the solid lattice. That is the lattice enthalpy. And we know that the enthalpy change from the gaseous ions to the aqueous ions is the enthalpy change of hydration of sodium plus the enthalpy change of hydration of chloride ions. So here this enthalpy change here is the enthalpy of hydration of sodium ions plus the enthalpy of hydration of chloride ions. So what we can say over here is that if we're starting with gaseous ions here, then we can convert the gaseous ions to solid lattice, that's the lattice enthalpy, and then dissolve the solid lattice to form aqueous ions. That is the lattice enthalpy plus the enthalpy of solution, and that is equivalent to the hydration enthalpies. Here we can go directly from the gaseous ions to aqueous ions. So we can say here that the delta H solution plus the lattice enthalpy, the enthalpy of solution plus the lattice enthalpy, is equal to the sum of the hydration enthalpies. This sum over here simply means we're adding up the hydration enthalpies of each of the individual ions. And since we just have 1 mole of each ion, we just have 1 times the hydration of sodium plus 1 times the hydration of chloride. So that gives us the same equation. Using this Hess cycle, we can derive the same equation. We can say that the enthalpy of solution is equal to the sum of the hydration enthalpies minus the lattice enthalpy. So now I solve the following question, which says, draw a simple energy cycle and calculate the enthalpy change of solution, or the enthalpy of solution of sodium chloride from the following data. They've given us the lattice energy and the hydration energies of the sodium and the chloride ions. So over here we want to figure out the enthalpy of solution of sodium chloride, right? That is the enthalpy change when 1 mole of sodium chloride dissolves in sufficient water to form an infinitely dilute solution. So sodium chloride solid is dissolving to form sodium aqueous ions and Cl minus aqueous ions, right? This is the enthalpy of solution of sodium chloride. And this is what we want to determine. So let's call that X. This is our unknown. Now they've given us the lattice energy of sodium chloride, or the lattice enthalpy, as well as the hydration energies or hydration enthalpies of sodium ions and chloride ions. Now, when we talk about lattice enthalpy refers to the energy released when the solid lattice is formed from its constituent gaseous ions. When 1 mole of the solid lattice is formed from its constituent gaseous ions under standard conditions, and hydration enthalpy refers to when these aqueous ions, each of these individual aqueous ions, are formed from the gaseous ion. So if we're going to draw a Hess cycle here, what we have in the third box are gaseous ions. We have Na plus gaseous, and we have Cl minus gaseous ions. The formation of 1 mole of the solid lattice from the constituent gaseous ions is the lattice enthalpy, that is minus 787. Whereas the hydration enthalpy refers to the energy released when 1 mole of this gaseous ion is dissolved to form aqueous ions. So we have 1 mole of sodium ions and 1 mole of chloride ions. So we have, this is the enthalpy of hydration of sodium ions, that is minus 406. And this is the enthalpy of hydration of chloride ions, that is minus 364. So we can say here that if we're starting with the gaseous ions, we can convert those gaseous ions to the solid lattice, and then the solid lattice can dissolve to form aqueous ions in solution, or we can go directly from gaseous ions to aqueous ions. So we can say that minus 787 plus X is equal to minus 406 minus 364. So therefore X is equal to positive 17 kilojoules per mole. Now, of course, over here we can also draw the energy cycle the following way. We start with gaseous ions. The energy change from these gaseous ions to the solid lattice is the lattice enthalpy of sodium chloride, that's minus 787. And the energy released when these gaseous ions are dissolved to form aqueous ions is the hydration energy of sodium ions and chloride ions over here. So we have minus 406 for sodium and minus 364 as the hydration enthalpy for chloride ions. So if we look at this energy cycle here, we're starting with the gaseous ions. We can go from gaseous ions to solid lattice and then dissolve the solid lattice to form an aqueous solution. That's this enthalpy change plus this enthalpy change over here. Or we can go directly from the gaseous ions to the aqueous ions. So again, we can say over here that minus 787 plus X is equal to minus 406 minus 364. And we get the same value for X, that is plus 17 kilojoules per mole. That's the enthalpy of solution of sodium chloride. Now let's look at the next example, which says that iron 3 chloride readily dissolves in water. Use the following data to calculate the standard enthalpy change for this process. Here, of course, we want to calculate the enthalpy of solution for iron 3 chloride, since 1 mole of solid iron 3 chloride is dissolving to form a solution of its aqueous ions. Now over here, we want to calculate the enthalpy of solution of iron 3 chloride, and they've given us the enthalpies of formation of iron 3 chloride as well as the products here, which are the aqueous ions, the iron 3 ions as well as the chloride ions. Now, since they've given us information about the formation enthalpies of the reactants and products, we're going to have over here is elements to complete our energy cycle. Since we have elements over here, we know that the enthalpy change of formation is when 1 mole of a substance is formed from its constituent elements in their standard states. Now over here, we're forming 1 mole of iron 3 chloride from its constituent elements. That's the enthalpy of formation of iron 3 chloride, and that's minus 399.5. So this is minus 399.5. The formation enthalpy of aqueous Fe3 plus ions is minus 48.5 kilojoules per mole. So this is minus 48.5 kilojoules per mole. And the formation enthalpy of chloride ions is minus 167.2. Now here we're forming 3 moles of chloride ions from its constituent elements. So that would be 3 times negative 167.2. So here we can go from elements to reactant and then dissolve the solid reactant to form the products. Or we can go directly from elements to the products over here. So we can say that minus 399.5 plus X minus 399.5 plus X is equal to minus 48.5 plus 3 times minus 167.2. And when you solve for X over here, we get X is equal to minus 150.6 kilojoules per mole. So that is the enthalpy of solution of FeCl3. Now, of course, since we're not asked to draw an energy cycle over here, we can also determine the enthalpy change for this reaction using this expression. We know that the enthalpy change for any reaction is the sum of the formation enthalpies of the products minus the sum of the formation enthalpies of the reactants. Here our products are Fe3 plus aqueous ions, and 3 moles of chloride ions. So sum of the formation enthalpies is 3 times minus 167.2 plus minus 48.5. So this is the sum of the formation of the products. Then we subtract the formation enthalpy of the reactants. We have 1 mole of FeCl3 solid. So we're going to subtract minus 399.5. We'll get the same answer. The enthalpy change will come out to negative 150.6 kilojoules per mole.